Hi everyone, my name is Anastasiya. I'm working as project coordinator and research engineer at EPFL. And today I'd like to present you a topic about 3D reconstruction of curvilinear structures from stereo images in microscopy. But first of all, I'd like to thank our organizers for this wonderful opportunity, and I also want to present the team I'm working with. So my project is called Sinergia. Actually, it's a collaboration between 4 different labs, but this part of the project I'll be talking about is a collaboration between 2 labs, Computer Vision Lab and Electronic Spectrometry and Microscopy Lab. What I want to talk about. So I'll talk about some general nuances of microscopy images. I'll talk about some general pipelines for stereo, what is stereo, why we need it. I'll briefly discuss some classical approaches and end-to-end deep learning methods. And then I'll present our solution currently we're using. So about microscopy. If you think about the world around you now and you look around, you'll see there are a lot of metals. And people from physics, they study their properties of these materials to make better world, to make materials more robust, to different changes, to temperature and things like this. And all this information about them, actually, it lives inside the atomical structures of those materials. And it's really amazing that nowadays it's possible to see atomical structure with the help of transmission electronic microscopy. So you can think about a metal is a range of set atomic planes. In a perfect world, they will be perfectly arranged, and if you put them through a microscope, you will see some uniform image, but nobody's perfect, so they're not. And there are some kind of defects in them. There are different kinds of. One of them I'll be talking about is dislocations. Recently, I heard a really nice example how to explain what is the edge kind of dislocation. You took a piece of cheese, you put a knife through it and leave it there. And this is kind of a dislocation because additional atomical plane appears there, and in microscopy images, it will be appearing as just a line. So the contrast will be different. The rest will be exactly the same. So why do we care about the defects? Basically, they determine the properties of materials, and basically that's why we need to know them, how to cope with them, how they appear in nature, and materials that are designed by engineers. But why do we care about stereo images? So in the world of physics, the 3D reconstruction is done by tomography. You take acquisition of multiple images, like 100 images, with small changes in a tilting. You have a specimen, you have a microscope, and you tilt it to the range of -60, approximately +60 angles, and you acquire all those images. The problem with that, it's really noisy when you do back projection, because in different conditions, it's kind of hard to find the right conditions to get really, really good images. It takes some time, and for acquiring 100 images, it will take forever. But it's what it's done, and it is what it is. So another problem with that, it's actually electronic beam that is used. It's done multiple times, for 100 times, and it can somehow break a specimen at some point. And the reconstruction will have some artifacts. I'll show you images a little bit later. So here in EPFL, there was another technique when you don't need to tilt the sample, actually. And so what's done? You have electronic beam that is going through the specimen. It's a really, really super thin of metal. And also the scales, it's like hundreds of nanometers. So it's electronic beam goes through the specimen. It gets converted into 2 beams. And that's the way you can think of 2 cameras that are looking at the specimen from 2 different angles. And this angle will determine our range of disparities. What's the goal of stereo reconstruction? You have the left image, right image, and you want to get this 3D structure of the world. In our case, of dislocations, how deep they are, how they look. So you can see some examples of images here. It's kind of hard. First of all, because even as the same specimen, under different rotation angles, will have different lighting conditions. So basically the contrast will change if you can see down. Also, it's a kind of textureless structures, which will be hard to match across each other. It's kind of really noisy sometimes, and those images, it's really hard to find the right conditions to obtain them, to have really nice images without some additional artifacts due to the acquisition process. So the structure of how it's done now, it's like this. It's manual. You manually segment both stereo images, you manually match them, selecting multiple key points, and you manually reconstruct it. It's super time processing. And now there is another work that was done at EPFL. It's a little bit better because segmentation is done semi-automated and the rest stays the same. What is a stereo vision in general? So we want to solve it, and particularly we want to solve the matching problem. There are two basic problems, calibration and matching. Matching is to find the right correspondences for each pixel. Stereo vision is applied everywhere. You can think about 3D reconstruction, an example of EPFL campus on the slide, in augmented reality, aerial mapping, architecture, and other stuff, and for structure from motion as well. The basic principles of stereo vision, for example, Mitra was talking about it, is epipolar geometry. Then you have triangulation. Once you know the camera parameters, when you know the matching of each point, you can triangulate back the 3D position of them. And another very important thing is image rectification. So basically, you don't want to search each correspondences for X, Y, and one image and for another. You want to have to search for the corresponding point on the exactly same line. You want to make it 1D problem. That's when image rectification came in, when you reproject on the same plane, common plane to the central line, and that's the way you get your rectified images. So also we want to have some additional constraints, because the problem is matching is kind of hard. So you can think about it of having unique matches, one-to-one matching. You can have ordering constraints, and you can think about it that you have to have both images and both points visible from each view. Some of them constraints may be broken once you have the occlusion. And one more concept I want to talk about is disparity. So I'll be talking a lot about disparity maps. It's just the difference between right and left pixels. So once you have the image close to yourself, the disparity will be larger. Once you move further, it will be smaller. Why it's really easier for us humans to estimate depth? Because we take additional informations. We have prior knowledge. We take the shape from shadings, from different textures, which information and from motion, which we don't have when we do reconstruction. Why it's really, really challenging. So you might have a transparent object, which it's hard to match. You can have multiple occlusions that are non-matchable. You can have microscopy images. You don't have their texture, almost no. You have low contrast, different contrast. You have a lot of repetitive patterns. In general, a stereo vision system looks like this. You obtain two images. You do the image rectification. We assume that you know camera parameters and camera poses. You do the rectification. You obtain disparity map. And then you do triangulation and create a 3D reconstruction. In terms of formulas, here is one really important. It's very general. So you estimate disparity or depth and you think about it as a minimization function. And here you have a cost, sum over the costs, and the other two terms are just smoothness constraints you should think about. General pipeline looks like this. You have first feature extraction, then you have to create matching cost and aggregated values, then you have to find disparity values, and then you can do some refinement steps. So first step is a feature extraction. You can use convolutional neural networks for this. You obtain left and right features and you use them further. It can be done two ways. You can do it one scale, fixed scale, or multi-scale. Another thing is the matching cost. This one is important. It is used in every architecture you'll see. It varies a lot. But the whole idea is you get a matching cost. Think about it as a 3D volume where you have two dimensions, image dimensions X and Y, and then you have disparity as a third dimension. And that's what you basically approximate at the end. You find the right disparity from this cost volume. It can be done two ways. One of them is a distance measure. And another way, it's a similarity learning network. So basically, either you take the distances L1, L2 over features you have, or you have some another network that gives you similarity matching score. One more thing that people are usually doing before putting for further processing is feature aggregation. It can be done via pooling, max pooling, average pooling, or it can be done via concatenation of features from previous branching. Pooling is preferable because you can get some kind of invariance. You can get multiple stereo view, not only two images, but multi-stereo view, and it doesn't increase the dimensionality. Another step that is done is cost-volume regularization. So why it's needed? Sometimes the things are broken, and sometimes your matching cost-volume will come out with some additional ambiguous values. So you need to give some additional information to the cost-volume. For example, segmentation maps, edge maps, some additional features, semantic features. Then you might have or might not have 3D encoder decoder, and then you have your finally regularized cost volume. Then you do disparity calculation. If you're not in terms of deep learning, it will be easy. It will be just argmin of your disparity range. But as we're in deep networks setup, we have to be a little bit smarter. We have to do soft argmin or soft argmax for that, or weighted if we want to have different range of disparities. And the last step will be disparity refinement. We need this because our disparity maps might be sparse, they might be obtained on lower resolution, or they have some other issues. There are really multiple methods to do this. I won't cover them, but you can read it afterwards in the slides. There are really multiple datasets for this problem, but there are some troubles with them. First of all, there are real-world datasets. They are really small, and the disparity maps there, they're really sparse. There are synthetic data. You get a lot of data, but it's synthetic. It has many images. It has disparity maps, everything, but it's kind of not real. And when you do a transfer learning or something, you get yourself with some troubles. In terms of evaluation metric, I'll be showing you some results. It's endpoint error. So you can think about just L1 distance, because we have already rectified images, and percentage of errorness. So you specify some threshold, and you want your results will be in the range of this threshold. It's just a difference between ground truth disparity map and the ones you've predicted. So there are some classical stereo matching techniques. There can be local, global, semi-global. The usual matching cost can be just as a sum of differences, or in classical approach, square differences, etc. You have different methods like SGM, MRF, and others. It's from classical methods. I'll cover only SGM because it's most popular, widely used. It's been there since 2008, and it was a really great trade-off between performance and speed. So here you can see the cost function really similar to ones you've seen before, the same cost volume, but then there is a smoothness term differs. Basically, you just have two penalization costs for the disparities that are close to the value and for disparities that are a little bit for the point that are a little bit further, and you take those several distances, several paths. You can from 8, usually choose from 8 to 16. You get this, you sum it over, and you get your score. And now I'll move to modern approaches. In 2017, there was a paper, GCNet. The basic idea that you put two images in a weighted semis network to deconvolutions. You get shared weights. You concatenate them. You get left and right cost volumes. Then you have a bunch of 3D network, convolution, deconvolution. You do soft argmax, and you get your disparities. And then you just compare them with left disparity, right disparity. You have ground truth, you have L1 loss, and you got the disparities with soft argmin. They were the best on their time. Later, PSM network came in. So basically, you want to have some context information, and a special pyramid pooling module does it. Also, they did a little bit differently. So they don't have shared weights after, they just create one cost volume, and they optimize it in a regression way. The rest idea is exactly the same. Also, the L1 loss changed in L1 smoothen loss. After that came sex stereo. So basically, here you're using segmentation information, and there are two different setups, unsupervised and supervised. For both of them, you use also photometric loss. So basically, you get your disparity map, you get some additional information from segmentation, it's also there in the loss, and you warp your left image with right disparity map, right image with your left disparity map. You got two images in this photometric loss, you compare them with your ground truth. There are some occlusion problems that it won't cover, but segmentation does the job really good, and they're really better results than previous. And the one really recent one, it's VPR 2019. It's an oral paper. It's called GANet. What I really like about them, they say, okay, we don't think that cost aggregation is done the right way. We want to improve it and to put it into deep learning terms. So basically here, as in typical STM, you have sum of matching cost and this smoothing penalties. And then the smoothing penalties parameters are defined by user, and there is a minimum that produces only zeros, and it's not really simple differentiable. So what they did, they specify some learnable weights, and they added them except of penalty terms. So that's why it became differentiable. Then they changed the minimum to maximum to remove also zero values, and also they put except of mean sum, which was proven that it's more effective and you don't get any loss in accuracy. And also they provided additional layer which refines structures and deal with downsampled accuracy. So here you can see the results. They're currently state-of-the-art in terms of disparity range. Disparity range can be in occluded and non-occluded areas. They're better in both. And I want to get back to our topic. So we want to reconstruct dislocations, very specific structures of atomic crystal. We had a problem. We didn't have data. So we had data. We had images from microscope. Done. That's it. We manually labeled them. Nobody provides any labels, both for segmentation and disparities, especially for both disparities, to check. And we did it this way. And we have our networks that does the reconstruction. So basically here you can see two images, left and right, and shared weights. In usual setup we want to do end-to-end learning, but here it's not. There is a two-step learning. First one, we're just training UNet with a typical way of binary cross entropy loss on results on segmentation masks. And after that we store the learned parameters for all the training and the test data. We store the last layers. Then we use those last layers to create 3D volume, encoder-decoder style, exactly the same. We got exactly the same cost volume, but then we had additional alignment layer, and with our disparity, predicted disparity, we do the warping for left and right images. So at the end, we have a lot of loss terms here. It's a loss term for segmentation, both of images, L1 loss for disparities, and then warping loss for both of images. And the last term is our consistency term. We checked these results in comparison with SGM. Here you can see left-right image, segmentation, disparity maps. And the first thing you see is there is really disparity. There are some shifts in the same two images that overlap. And on the right is our predictions. It's a reconstructed image, left image with right disparity and vice versa. Then we say that, okay, we want to evaluate the results some more. And we labeled some more data, different types. Inspire dataset, retina, blood vessels. We got exactly the same thing, so there is a reconstruction result in the bottom. Also, we evaluated our method. Okay, it's really small, super small, even with the augmentation, it's super small. So we took the fly-in things, we extract their edges and evaluated on them as well. And again, we got really, really good results, better than other methods. And now I want just to show the reconstruction. So on the left you can see aligned image, how it looks. Approximate angles, they're not perfect. And you can see the reconstructed ones. So that's the results of our reconstruction. Thank you for your attention.
Thank you for a great presentation. So questions?
Have you tried combining more than two images? For example, if like we have like 3 angles or 4 angles, that should be possible to see more details, or if they are hidden in like one direction.
We really want to try it, but we're at the process of acquiring data. It's really hard and not that easy to get them. We don't have enough data yet to try it, but we will.
Anastasiya, thank you for a nice talk about stereo vision. And As a person who does stereo vision practice, I was just wondering about confidence measures. And how sure are you in your reconstructed depths from these stereo images? How do you measure whether this this label is valid or not?
It's a really good question. Thank you for your question. We're not quite sure. We are going to compare results with tomography, which I've told not perfect, but it's the only ground truth we have. Another way, we'll try simulated images. We'll have some kind of bringing their reality or in the process of it. That's a really good question. We're working on it.
More questions? Okay. I have actually a question. Like I am really curious. How do you label the disparity? So how do you instruct people to do such kind of tedious labeling?
So basically, you get your segmentation results, then you copy them to the second image, and you just manually label them. So there is sure some error, some kind of error for sure, but there is no better way, unfortunately, to do it.
No, I understand manually, but do you have some special software?
So we just use open source tool Label Me with a little bit adjustments, but that's it.
Thanks.
So as I understood, you could use tomography results as ground truth. Why didn't you use it from the beginning as training data?
Because it's only one pair of images. We have this tomography data, and it's really hard to acquire. We have a lot of, so the data we trained on, it was multiple different, so several different materials and dislocation changes there, which is impossible to get the tomography data for.
Thanks. Other questions? If not, you can have a 3 minutes bio break, and we will go to the next speaker. And in the meantime, I would like to thank you again for Nastya. And one more thing, what is the best question?
About evaluation, yes. Question about evaluation.
Okay, thank you. Okay, he already have one book, another one.
Okay, the first question then.
First.
There.
Yeah.